Okay, so hi everybody, and welcome to the last day before your exam. So our goal is to take care of some logistics stuff to make sure that you've got the information that you need to make sure that you show up in the exam, and also to address questions that you may have on the 2015 exam, if you have any, or if not, any questions that you may have on other topics. So just to remind you, tomorrow, and of course I have to recalibrate every single time. So tomorrow at 7:45, all your bright shining faces will be there, and you will have in hand a calculator with batteries, correct? And number 2, pencils.
Sorry, walked off with it.
That's okay. It's nice to know that somebody besides me does this. So these things, and then I will be there to greet you with brain food. Carrots. Celery. Celery and meat. Yes. Yeah. Definitely not. All right. Now, last night you took a look at the 2015 exam, 3 response questions, and you said, "Hey, I've seen all these," right? And so, do you have any questions about them?
I feel like we've done so many talks, I just don't have any questions anymore.
Good. Fantastic. I win.
It's almost too competitive.
Yeah, I hear that.
No, like even like throughout the past years, it just all seems like the same thing.
Yeah, good. That's encouraging because that means that there's a high probability that you'll look at 6 or 5 questions tomorrow and you'll say, "Hey, these are pretty familiar kinds of questions," because in the end they're all asking you to do the same small set of theorems.
If you do, I think I have questions for you.
Yeah, absolutely. Yeah, let's take a look. 2015, number 4. We have a differential equation here. And of course, as soon as we see a differential equation, our first thought is the slogan, separate, integrate. But then I look at this and I realize this is not separable because it's not in the form f of x times g of y. And because it's not separable, I'm clued into the fact that I'm not going to be able to find an explicit solution for x and for y as a function of x, and so I'm not even going to bother. Instead, I'm just going to follow the directions and throw theorems at this thing until it surrenders. All right. On the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. It's a simple matter of plugging in points. I've got x equals 0, y equals 2 at this point, so I get a slope of -2. I've got x equals 1, y equals 2 at this point, so I have a slope of 0. I have x equals 0, y equals 1 here, so I have a slope of -1. You don't have to be very precise, just make your -1 less slopey than -2. And then at this point, 1, 1, I have a slope of +1. No dots there, no slopes there. At the point 0, -1, I've got a slope of +1. And at 1, -1, I have a slope of 3. Nice and slow. So I've got my slope here. Find d squared y dx squared in terms of x and y. Determine the concavity of all solution curves for the given differential equation in quadrant 2. Give a reason for your answer. We remember that the in quadrant 2 part is a little tricky. So I'm going to begin by doing what they say, which is to find d squared y dx squared. And of course that will be the derivative of dy dx. Let me take and copy this over to the whiteboard so we have enough room to work. So the d squared y dx squared is going to be the derivative of this thing. which is 2 minus dy dx. But we notice that this is verboten. We must have an answer in terms of x and y, so we can substitute into past. And that means that I replace dy dx with what it is, and when the dust settles, that gives me 2 plus y minus 2x. So here's this. The second part of that question asks me to determine concavity, so I'm going to look at the second derivative, specifically its sign, of all solution curves in quadrant 2. Everybody point with your finger, where's quadrant 2? Right there. So we're over here in quadrant 2 right here, and I wonder what's up with the sign of f double prime in quadrant 2. Not obvious, so let me pick an example point to try to get my head straight. Let me pick maybe, how about -1 comma +1? And I go and I plug -1 comma +1 in here, just to get an idea of what's going on, and lo and behold, I see what's going on. A positive y and a negative x are going to give me a positive second derivative every single time. Every single time. An example is not true, so I'm not going to use this as part of my reasoning. This was just for me to get an idea of what was happening here. Instead, I'm going to argue generally. I'm going to say that d squared y dx squared at xy is going to be positive when y is positive and x is negative, which is another way of saying in quadrant 2.
Can you just say embedded quadrant now?
Yep. And then, of course, I need to make sure I answer the question. How do you go? Yes.
I have a question. Some questions say, like multiple choice, they give us a sketch and find a natural equation.
See if you can find one of those, and then we'll finish this question later. Okay. All right. In C, let y equal f of x be the particular solution to the differential equation with the initial condition f of 2 is equal to 3. Does f have a relative minimum, relative maximum, or neither at x equals 2? Justify your answer. We are going to avoid the newbie trap. We are not going to look at one word and think, aha, I know what I'm doing. We're going to actually read the question. Does this question say find the particular solution? No. That's good, because I can't with what I know at this stage in the game. But y equal f of x be the particular solution. Here is my question. Does f have a relative maximum or neither? What are my possible tools for this job? First D test or the second D test. That's right. And the first D test requires me to do a change in sign of dy dx. That's going to be tough here. The second D test is very appealing because I can evaluate first and second D right at x equals 2. So the second D test is my choice because it allows me to evaluate at the point instead of having to pick values that are on either side of x equals 2. Does that make sense? So I'm going to march in with the second D test. What does the second D test say?
If f, okay, if f double prime is positive, and I do know it, and f prime is positive, is inclusive, has a local max.
You're just going to keep on saying that.
Zero, it's zero, yes.
Of course it has to be 0. Why? Because local extrema
Only occur at
critical points, of course. So if f prime is 0 and if f double prime is positive, then
it has a local
min. And if f double prime is negative,
yes, and f prime is 0.
local max. And what if f double prime is 0 or fails to exist? Test fails. Good. All right. So let's apply that right here. So in part C, we're going to check f prime first. dy dx at the point 2 comma 3 is equal to 2x minus y equals 1. What do I conclude?
The slope at
There's
that
no,
point is
there's no local minimum, local extreme.
In other words, answering the question that's asked,
There's neither,
neither, exactly.
neither functions have local extreme.
Yep, because local extrema only occur at local points. Yeah. If I had gotten 0, then I would go on to check the sign of d squared y dx squared. But this question was intended to catch people that only look at f double prime without first checking f prime. That's why you have to know both conditions. On the curve y equals x squared, there are an infinite number of points where d squared y dx squared is positive. But there's only one local min where y prime is also equal to 0. Everybody see that? So don't be the sucker, check both conditions. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. This is a sophisticated question, but not a hard question. It requires us to observe some terms. First of all, what does it mean to be a solution? It means that it actually satisfies the differential equation. So in other words, if I check y by plugging it in, I will find that dy dx in fact does equal 2x minus y. That's what it means to be a solution. Second of all, it's going to require us to observe that in order for two things to be equal, their coefficients have to match. For two polynomials to be equal, their coefficients have to match. So let's actually take this over here. The spirit of this problem is that the differential equation as given, which is 2x minus y, is going to have a lot of different particular solutions. Most of them are going to be curvy, but one of them, apparently, according to the problem, is actually going to be a straight line. And I need to find out what straight line that is. Okay, so here we go. Since dy dx is equal to 2x minus y, and since y is also equal to mx plus b, it makes a whole lot of sense for me to go ahead and compute dy dx. What is dy dx equal to? And so now, if dy dx is in, then gosh darn it, dy dx is in. Okay, and this is our equation. Now the second thing is we observe that the right-hand side is a first-degree polynomial, or a straight line. And the left-hand side is a zero-degree polynomial, or a constant. If two polynomials are to be equal to each other, they have to have the same coefficients. And that means that the coefficient of x on the right-hand side must equal the coefficient of x on the left-hand side. That term is invisible. What's its coefficient? 0. So that immediately tells me that 2 minus m, which is the coefficient of x over here, equals 0, which is the coefficient of x over there. And also, the constant terms must be equal to each other. So that tells me negative b is equal to m. And now it's pretty obvious what the solutions are. M is 2, and b is negative. In retrospect, it seems kind of obvious that we should have had a slope of 2. But now, let's come back and actually check that we did it right. Y equals 2x minus 2. We claim that's a solution to our differential equation. Let's check that by plugging in. dy dx equals 2. And does that, in fact, equal 2x minus y? We'll look at that. It sure does. So it all checks out, and we're happy.
What did you do the last part?
I just checked. dy dx is 2. And if I did it right, then dy dx should be equal to 2x minus y, and it is. They didn't require you to check, but of course, as a smart student, I want to make sure I get it right. So this last part here was somewhat sophisticated, but it's actually a very common move in the solution of differential equations. So when you take a Division Q's class in college, you will actually probably do a whole lot of this. Now, it kind of depends on what you're doing with your life. Yeah.
How did you get the animal?
Here, I computed dy dx and found that it was empty.
And then like, the next step, the 0 equal to like 2 minus m.
Okay, yeah, so this is the important thing. I have a polynomial over here. Let's write this as ax at a1x plus a0. Okay? a1x plus a0. And that's equal to another polynomial over here. Let's write that as b1x plus b0. Now b1 is 0 in this case, right? It's invisible. If I've got two polynomials that are equal to each other, their coefficients have to be equal. A1 has to be a b1, and a0 has to be a b0, if they are going to be equal for every value of x. Think about two straight lines. If I have two straight lines that have exactly the same coefficients, those two straight lines will be on top of each other. They will be equal for every value of x. If I have two straight lines whose coefficients are not equal, they will intersect, or they will be parallel. Equal only at one value of x, or equal at no values of x. So the only way for these two to be equal at every value of x is for their coefficients to be equal. And so I set the coefficient here equal to the coefficient there. And I set the coefficient here, the constant, equal to the constant coefficient there. This technique we call matching the coefficients. Yes? Good. Are there any other questions, either from the 2015 exam or from the table?
Would the letter
Uh-huh.
A skip where from the administration?
They will actually provide in your test booklet a copy of that grid.
I don't understand the language of 6B.
Question number 6, part B. Okay. Wow, a whole lot of implicit differentiation stuff this year. Okay, consider the curve consider the curve given by the equation blah. It can be shown that dy dx is equal to blah. That's nice. I don't have to do the mechanics. We like that. I'm going to go ahead and do A, B, and C, just because. Write an equation for the line tangent to the curve at the point -1, 1. I need slope, I need point. I've got a point, so I just need dy dx. dy dx at the point -1, 1 is going to be here. Make sure you use that. +1 is y over 3 times 1 squared minus -1, which is 1/4. Slope, I have a point, y minus y1 equals slope times x minus x1. Yay.
You don't have to put y on its own, right?
No, you don't.
Okay, because on like solutions, they always have it on.
Yes, if you think about it, there are 3 different ways that we could write this line, and so they're going to pick one in the solution guide. But anything that is algebraically equivalent to the correct answer is correct.
Could you like make it complicated on purpose?
You can make it complicated on purpose. You run the risk of your grader either becoming annoyed with you, or worse, somehow making an algebra error to determine if it's equivalent. There is a Durant son, the third one, who found himself in trouble in the 6th grade because he was asked to give equivalent fractions to 3/4. And so he gave answers such as the square root of 36 over the square root of, oh, I don't know. Yeah, the square root of 64. Yeah. And so then the teacher had like puzzled her way through equivalences there. Part B, find the coordinates of all points on the curve at which the line tangent to the curve at that point is vertical. Jackson, make your way as far as you can through that language and tell me what you understand of that question.
The line tangent, I know the not is over, was 0.
Okay, so we got two things going on. One is we need to know the difference between horizontal and vertical. Yeah.
Vertical is this way.
Yes.
I don't know if that way.
Yes. So if you have a line like so, then what is its slope?
No, 0.
0. And if you have a line that is vertical, what is its slope?
Not
It does not exist.
Not.
Good. There you go. You just had to think through. You knew what horizontal and vertical meant, but you had not thought through what are the slopes of these two lines. I want to actually do this because sometimes there is a trap here. If I want the tangent line to be vertical, then that means I want the denominator of dy dx to be 0. So I set that denominator equal to 0. And when I do not get numbers. Instead, I get a relation between x and y. Yes, very good. What that relation does is to give an additional constraint on x and y, and the original constraint is given by the original equation of the curve. I now have two constraints on x and y for my two variables, and substitution tells the tale. If I now plug in, then I get, I'm out of room here, so let me copy all this over. Y cubed minus xy equals 2. dy dx is equal to y over 3y squared minus x. So I set 3y squared minus x equal to 0 so that x is equal to 3y squared. And now, if I substitute back into the original right here to find my points, then I get y cubed minus 3y squared y is equal to 2. And would you look at that? They made the problem nice for me. They put an Easter egg in the problem, and that is that I end up with negative 2y cubed is equal to 2, or y cubed equals negative 1. And that is a simple solution. What's the single value that works here? Y equals negative 1. And because y is equal to negative 1, then x is going to be 3y squared. And I package my point, put a box around it, and move on with my life. I box my answers, yeah. Or underline. Kind of depends on my mood. In part C, they ask us to evaluate d squared y dx squared at the point on the curve where x is negative 1 and y is positive 1. And wouldn't you know it, that means that we've got to do some implicit differentiation after all. So here we go. We're going to roll up our sleeves. Everybody roll up your sleeves. And we're going to take the derivative. D squared y dx squared is equal to the derivative of dy dx. Make sure I copied that correctly. Yep. And so now we all run through the song. Please no singing out loud during the exam. Low, high, less high, low. And now when I take the derivative of this guy, don't forget your chain rule. 6y dy dx minus 1. And all of that over 3y squared minus x squared.
Ready to plug in the next one.
Or not.
Or we already found you right there.
Bingo! Yes! That's why we did part A. We can look ahead a little bit and see that if we,
Oh, it's the same point. Oh.
yes, if we plug in the expression for dy dx here, we will end up with a horrible expression that we will then have to substitute for. No, don't do that. General rule of thumb. The good people at AP understand that you only have 15 minutes per question. They will not give you a question that has to be done with horrible algebra. There will be a way to make it simpler. And the way to make it simpler is to recognize that all the way up in part A, at the point -1, 1, we found that dy dx was equal to 1/4. We did that for finding our tangent line. And that means, since we have differentiated, we are eligible to plug in, and so we are going to do so. In our expression, the dy dx, this is poorly written, let me tuck this off to the side here. There we go. Our expression for dy dx is 1/4. All over, 3 times 1 squared minus -1 squared. Yes, this is a number. Stop here. If your inner nerd feels compelled to simplify it, tell them, shut up, I'm in a hurry, I'm going on to the next question. Sometimes you have to speak to your inner nerd. More often I have to speak to my inner slob, if you know what I mean. Because my inner slob is trying to kill me. But occasionally the inner nerd is also trying to kill me. This is the point where you want to tell the inner nerd, do not simplify this, because you don't get any extra points for simplifying it. And if you do it wrong, you just turn the right answer into a wrong answer. The only reason you would simplify is if you need that value for something. Jackson, better?
Yes.
Good. Any other questions? About anything? We've got about 15 minutes here. So, calculus Jeopardy. The answer is 2x.
What is 2x?
What is 2x?
That's pretty good. What could be other questions that go with that? What is x equals 2?
2x.
Are we gonna have a
What
party?
is the derivative of x squared?
What's the integral of 2 plus or x cubed?
Not the, but and.
And integral.
What is their x cubed? What is their x cubed?
What is their x cubed? Why is there x cubed?
No, like you said, integral of the x squared. So what is their x cubed?
What is the what is n antiderivative of 2, or what is the derivative of x squared? Don't worry. It was just silly. It was a rabbit trail.
Are you gonna have a party after tonight?
T-Pay, looks like you have a question. Yes, good.
Oh, right. Do we know what
The difference quotient will show up occasionally. The difference quotient is just a fancy name for average rate of change. So our scenario often involves numeric data. I might have, for example, time and velocity, like so. And maybe my time is 0, 1, 2, 3, 4, and my velocity is 6, 12, 13, 10, and 2. Okay? Something like this. And I might be asked the question, estimate the acceleration at t equals 2. First, I want to observe that the acceleration is the derivative of the velocity. So what they're really asking me to do is to estimate v prime of 2. And because I have numeric data, the only way that I can estimate that is with a difference quotient or an average rate of change. So I'm going to say that v prime of 2 is approximately equal to, and the most reliable average rate of change will be found by bracketing on either side of 2, so that I have v of 3 minus v of 1 over 3 minus 1. See our average rate of change there? And that's going to be 10 minus 12 units meters per second over 3 minus 1 seconds. And of course, that's a number, so we're done. Or if I need that number, I would simplify it to negative 1 meter per second per second. Yes?
I was thinking of like the formula of the limit,
So let's compare and contrast the difference quotient with the definition of the derivative. Yeah. The definition of the derivative also uses a difference quotient to compute an average rate of change, but then it makes that average rate of change instantaneous by taking the denominator and shrinking it to 0. So that we have f prime of c will be the limit as x goes to c of the difference quotient. So here I have an average rate of change for a function at point c, and now I'm going to take that average rate of change and make it instantaneous by shoving x towards c. And when I do that, my secant line down. Okay. So the difference between instantaneous and average rate of change is the limit process. If I wished to rename all of my points, so let me call this guy x, and I'll call this guy x plus h, then I get the exact same result, but things juggle around a little bit. X minus c would now be x plus h minus x, which is h. So this will be the limit as h goes to 0 of difference quotient x plus h minus x would be h. And there's our other definition. If you compare and contrast that with what we did here, what happened here was I did my very best to estimate that limit with the information that I had. Does that help? This quantity also shows up in what famous theorem? The mean value theorem, that's right. So the mean value theorem gives us a little bit more information. It tells me that assuming v is continuous and differentiable, then somewhere in the time interval 1 to 3, I will get an acceleration that is exactly that number. Good. Any other questions? Oh, you're shut up.
So inverse function theorem is inverse prime is equals to 1 over x prime evaluated at inverse.
Yes, that's exactly right. So let's take a look at that briefly. In the larger world of calculus, the inverse function theorem shows up in some surprising ways. As far as we're concerned, for our purposes, the inverse function theorem has a tendency to show up, especially when we are looking at functions that we cannot evaluate the inverse for directly. And I'll give you two examples. One of those was, I think it was question 27 maybe on multiple choice. And we were given f of x is equal to x cubed plus x, and then we were told that g of x is the same as f inverse of x. And they asked us now, given that g of 2 is equal to 1, find g prime of 2. Okay? So this is really a question about the derivative of our inverse function. And this is particularly relevant when I can't find the inverse function directly. If my function had been simple, like f of x equals x cubed, then I would just say f inverse equals the cube root of x and find that derivative directly. That would be easiest. But here, f of x equals x cubed plus x, it's not obvious what the inverse function is, so I can't find a formula for the derivative explicitly. So instead, I'm going to use the inverse function theorem. So, what does the IFT say? F inverse prime equals 1 over f prime, evaluated at f inverse, just like so. All right. So now, since G is f inverse, I can rewrite this for our problem. Let me do that over here so you don't confuse this. Here's our form. I can rewrite that as G prime of x equals 1 over f prime of G of x. Just replacing f inverse with G. And G prime of 2, which is what I'm interested in, is going to be 1 over f prime of G of 2. And wouldn't you know it, they told me what G of 2 is. That's the key to making this work out, is that I will have to know the value of the inverse at the indicated point. So I replace G of 2 with what it is, which is 1. And now I ask, can I find f prime of 1? Well, yes, I know f. What's f prime? 3x squared plus 1. What's f prime of 1? 4. And therefore, we're done. And that's it. This was the multiple choice problem that presented itself. Here's another common format where you might have x's and f of x's and f primes of x. And let's just make up some values here. And let's make this like 6, and 3, and 1, and -2, and -4. And should my f prime values be positive or negative for this function, do you think? If you had to guess, I'd say negative. Yeah, so let's make it -2, maybe -3, -1, maybe -half. Sure. Whatever. All right. Now, let's pose a question. What is f inverse prime of 3? All right. So this is the question as posed. Notice that this is a little bit tricky because we've got a couple of different places where we have some 3's going on here. And so we're going to have to use the form of the inverse function theorem in order to make this all work out. Everybody give me the form. F inverse prime of x equals
1 over f prime evaluated at f inverse.
Excellent. I recommend just writing the form first to keep your head straight. And now, if I want that at 3, then it's going to be 1 over f prime of f inverse of 3. There's my form. It's on the page. Now I get to think. What is f inverse of 3? Yes. Notice that f of 3 is -2, which means that f inverse of -2 is 3. That's not what I want. But notice that f of 1 is 3, which means that f inverse of 3 is 1. That's what I want. There can't be. Because a function that is invertible must have exactly 1x for every 1. It must be a 1-to-1 function. That's a great question. And that goes to the heart of what kinds of functions have inverses. Only 1-to-1 functions. Not only 1y for every x, every function is like that, but also 1x for every y. So, having found that f inverse of 3 is 1, we now replace f inverse of 3 with what it is. Now we need f prime of 1. Back to my chart, it's -3. And we declare victory and retire the field. Go. Another problem. Yes. Yeah. Just.
Referral out. Like 2011 number
2011 number 2C. Let's take a look. Ah, numerical integration. Aha. Yep. I want to compare and contrast these two problems. We're given a table, and we are asked in part B to explain the meaning of 1/10 the integral from 0 to 10 of h of t, and use a trapezoidal sum to estimate that integral. I'm assuming you're okay with that part, but let's walk through it just in case. With a trapezoidal sum, I want average height times width. The average height here is 8456. Yep. And 8. No. Yes. 48. Wow. I'm having a hard time. And 43.5. Those are my average heights. And my widths are found by going through and computing delta t's. What's my delta t for the first interval? 2. The next one?
4.
And 1. All right.
And then,
Yeah. Okay. So, the integral of h of t then is going to be average height times width. I need space to work. I had wanted to avoid this, but 0, 2, 5, 9, 10. And 60, 66, 60, 52, 44, 43. 60, 52. Giving me average of 63, 56, 48, and 43 and a half. So that the integral from 0 to 10 of h of t times 1/10 is going to be 1/10 of, and now we're going to go through and do average height times width plus 56 times 3 plus 48 times 4 plus 43.5 times 1. And AG, what am I going to do? Answer for her. Be done. That's right. We're done. That's a number. Stop. Okay. Now, we do have to interpret this. So what is the meaning of this integral expression right here? It is the average value of h. But the average value of not h, but what h represents, the temperature of the T. Okay. In degrees Celsius, because I have to use the units, and what else is missing? Not at t equals 0, but on the
I
interval.
was gonna say that at the time 0 is less than or equal to t, which is less than or equal to 10.
Yep.
Is that, okay.
That is right.
So they'll always give you points for next certain form, at least correct?
Yes. Yes.
It's not like a matter of personal
Nope.
opinion, like you guys just said.
We unlocked the form. Now, when we look at part C, something strange happens. And that is that they ask us to evaluate the integral from 0 to 10 of h prime and interpret it. And Justin, here's our problem. I don't have a table of values of h prime. Bing, bing, bing. Fundamental theorem. Justin, if I apply the fundamental theorem to this integral, what do I get?
Oh,
Yep. H of 10 minus h of 0, and I'm pretty sure I can find those values. Why? Yes, I can. H of 10 is 43, h of 0 is 66,
That's a number.
and that's a number in degrees Celsius. What does it mean?
The total change is the same right now. Total change in the interval,
no, from time t equals 0 to time.
the interval t,
But the total change in what?
Oh,
temperature.
Temperature. That's what h represents.
Oh, yeah.
And there it is. So the moral of the story is, there's more than one way to look at an integral. You can look at it from the lens of adding up trapezoids, rectangles, what have you, or you can look at it from the perspective of the fundamental theorem, which takes all of that adding up process and hides the details into the antiderivative. Okay? You guys have learned a lot. Yep. I'm proud of you. Go to it. Earl, I'll see you tomorrow morning.
Yeah. That's something like after homework? Okay.
No. Show up because you won't have time if you do that.
Okay.
You're gonna need the full time. So I'd say 8 o'clock Eastern.
I know, no, I'm
Okay.
gonna find you.
My
I'm
car
gonna find you.
we don't get here till
Yeah, where should we be?
8:05.
All right. Well, if you're there a little bit late, it'll run over. And you'll say,
Oh, see that? Wait, do we?
What are you watching?
But today I think there was no information about, I don't think there is.